Hey, Dr. B here again, and let's take a look at the electron configuration of atoms around a nucleus, but let's add a detail to it known as orbital notation. This will tell us a little bit about the direction the electrons are spinning in and how they will try to spread out whenever possible. After all, they all have a negative charge, which means they're repelled by each other. This will give us a little better idea of where the electrons are. Let's start with a 3-electron system such as lithium. If you grab a periodic table, you should know that the electron configuration is 1s2, 2s1, meaning the first two lowest energy electrons are close to the nucleus in a spherical shell. That third electron is out in a shell of higher energy, further from the nucleus. It's spherical and it holds that one electron. Let's add to that one level of detail known as orbital notation, which simply means that for each orbital group, that means a pair of electrons, draw a box with an up and down arrow. And in this case, we don't have to draw the bottom arrow because there's only one electron. This simply says that that's our electron configuration. This is the orbital notation, and the arrows imply a spin direction. The Pauli principle, as determined by Wolfgang Pauli, is that when electrons are paired up, and they are a lot, they will do so with opposite spins. So now that's electron configuration with orbital notation. Let's apply it to a larger system. How about a 6-electron system, like carbon? The electron configuration, as you probably know, is 1s2, 2s2, 2p2. And let's draw a box for each s orbital. Good. Now for the p orbital group, it can hold a total of 6 electrons. So I encourage you, whenever you're drawing the the orbital notation for the p orbital group, draw all 3. The reason is because when you throw those 2 electrons in, you might be tempted to do that, but this would not agree at all with experimental evidence. In fact, electrons tend to spread out within their orbital groups, so draw them more spread out, like that. This is applying what's known as Hund's rule. Electrons will spread out within orbital groups. Those people with a deeper understanding of it know that even this model does not agree completely with reality. I'm talking about a concept known as orbital hybridization, but for the purposes at this point, this is the electron configuration of carbon with orbital notation. Fine. Let's bring it out to a much larger system, 16 electrons. First draw the electron configuration, 1s2, 2s2, 2p6, 3s2. For each s group, draw 1 block. For each p group, always draw 3 blocks since it's a 6-electron system, and apply both rules that you've learned. The Pauli principle, which is easy, just put in little arrows with opposite spins, and Hund's rule, which means when you get at the end, try to spread them out as much as possible. Why do I only say at the end? Well, it always fills up in the Aufbau order. These will always be full as we go from low energy to high energy, so there's no spreading out necessary because they're absolutely full. But when you get to the last group, spread them out. This is the electron configuration with orbital notation for sulfur, applying both the Pauli principle and Hund's rule.